Yeah, I'm going to record this session. And let me put some comments. Using I'm recording this session. So for those who cannot attend today, I know this is a Good Friday. So I have set up a practice exam 2 in Blackboard. Please take the exam today. Okay, let me tell you what is involved. I have set up 3 folders. Number 1 is the exam, dummy exam, but you have to go through it today to save you time next Monday when the school computers, everything come back to life Monday. Everything is real now, the exam, real exam. So the first file I created in Blackboard is the test exam. You can take it remotely. Then after you successfully log in, answer the short questions, it shouldn't take more than a few minutes. You sign your name in the answer because this is what I like you to do in the real exam. That is for you to acknowledge the School of Engineering's honors code. That means you did not receive help from anybody else. You did not give help to anybody else during the exam. And the second folder I created is for you to submit a handwritten homework, dummy homework problem, whatever you wanted, or anything. Submitted just like you submit a homework. I created for submitting your exam papers. And the third folder is created for communications among us during the Monday, during today. I set up for today, but over the weekend, I'm going to revise it. I'm going to maybe eliminate and change it to the real thing now. The forum is designed for communication among all of us during the exam. So if I have a typo, a possible typo in the exam problem, you can allow me to make sure to clarify if I made a mistake or not. Then I open my response to everyone. This is a point raised by a student in another class. This possibility can happen. So I create a forum for the exam. If you have any questions during the today, you can put it in there, activate forum. The forum can be open on the separate window. I set up that way so it will not interfere with your exam. You can occasionally go to the forum, see if I make any announcement. Okay, so this is the way we set up for the practice exam. Trust me, this is a high-tech exercise. A lot of things can happen. Murphy's Law. Anything happen will happen. Yesterday, I had a practice exam for another class which has 63 students. You're not going to believe I just sit here all day long to answer questions. There are three or four outstanding issues I have not resolved yet. A student claimed, for example, I have a weak internet connection. What should I do? Proctorial keep logging me out, kick me out. What should I do? I'm not a computer expert. I'm not an IT person. School is officially closed today. So we will not get much help today or in the next 2 days before the exam starts. So I will do as much as I can. Other than that, I urge you to take the practice exam, go through the exercise, answering the short questions, and then leave the exam folder, then submit your dummy homework to the submission folder, and also get into the forum, see if you can leave a message to everyone. So this is the exercise I would like you to go through today. Make sure you can go through the process without any issues. And for the exam, we have another faculty in my department who gave a exam yesterday, and his experience is we need to enhance the time. I reduced the number of problems from 3 to 2, but I still put a safety factor. I increased the exam time, I will, from 60 minutes to 90 minutes. So you should have plenty of time to do these 2 problems. Okay, so this is the special issues I want to tell you. Any discussions? Only 2 problems, not 3 problems, Mitch. For 90 minutes. I should have put a smiling face. Any questions? You have been quiet. Can you hear me?
Yes, sir.
Yes,
Yes, sir. We can hear
Mr.
you.
Tsai.
We can hear you. We can't hear you.
You cannot hear me?
We can.
Oh, okay, good, good. Do you have any questions?
Yeah, we can hear you.
Okay, like I discussed last time, it's been a while since you guys took the last exam, so it covered quite a lot of material. Basically, we are dealing with, let me see if I can find, let me share the screen. I think I have this. Okay, before I go through that detail, Chapter 3, Chapter 4, Chapter 5, Chapter 6 are the main topic we'll talk about since the first exam. Chapter 3 and Chapter 4 deal with first law. And Chapter 3 deal with closed systems. What are the 3 typical closed systems in this course? I mentioned 2, I emphasized 2, but I should add third one. The first one is you have to make judgment because this is really very important. Closed system, by definition, no mass in, no mass out. So there are 3 typical type of closed systems. In a rigid container, gas or fluid, even two-phase fluid in a rigid container is a closed system, no mass in, no mass out. Second type, fluid in a piston cylinder device. Number 3, do you notice the author discuss heat engine, heat pumps in closed systems in chapter 3. It's because if you take heat engine as a whole, even within the heat engine, there are 4 steps in a cyclic process. Heat engine as a whole, if you take a bird's view, it's a closed system. The steam in the heat engine doesn't go out, doesn't go in, right? It may go through 4-unit operation. So in many examples, the authors treated heat engine, heat pumps as closed systems, fluid as a whole. So that's chapter 3. Chapter 4 deal with open systems. By definition, open system means there are fluid coming in and going out, right? It's the definition of open systems. So what are the typical open systems? A pump, a turbine by themselves. A pump by itself has a fluid coming in, fluid going out. A compressor does the same thing. Turbine does work. It has a fluid coming in and going out. If you take the control volume like this, the boundary of the system, you have to clearly define the system boundary at the outset in your analysis. If you are given a turbine, for example, the turbine by itself is an open system because steam comes in and it leaves at the other end. Okay, now if you understand chapter 4 deals with open system, then there are two categories of open system. Open system can run in the steady state. That's the first half of chapter 4. And the second half of chapter 4, the authors discuss unsteady state. Unsteady state operation can be, there are only two examples. They also give us only two types of problems. Filling the tank. If a tank is totally evacuated at the beginning or half filled, then we connect the tank with a high pressure line, fill up the line to certain pressure, fill up the tank with certain gas at a high pressure. And the second type of transient state operation is accumulator. The steam leaves the accumulator in the morning when we need to generate more power. So fluid leaving the container is considered a transient operation. So this is chapter 3, chapter 4. Chapter 5, we start introducing the basic concept of second law. We discuss irreversibility. We discuss how the reversibility can be applied to heat engine, heat pumps. And then we can define the thermal efficiency, the COPs, etc. That's chapter 5. Now, chapter 6, we start introducing entropy. So you are responsible for the first half of the discussion of entropy. Entropy is very important. By definition, is entropy change is change in heat transfer divided by the temperature for the reversible process. Even for irreversible process, we can still estimate the entropy change based on the concept that entropy is a state function. So as long as we know the initial state and the ending state very well, we know the entropy change. Even the process depends on the past. It's an irreversible process. So if you can do the homework problem up to what you submitted this week, you should be fine. Then chapter 7, the coming attraction, is going to involve open systems, entropy analysis, entropy balance for open system. Chapter 3 and chapter 6 deals with closed systems, container, cylinder, and heat engine, heat pumps. Those are the material we cover. So in order to analyze a problem, what do? I give you let me see if I can activate. Okay, I can share the screen with you. Just 1 minute, give me. Did I close this? Okay, I can share the screen. Okay, now you can see this is the email I sent to you 3 days ago, 4 days ago. To analyze a problem, first you have to choose the system. Usually it's very obvious. For this course, it should be very obvious. It's a tank, it's a fluid inside a piston cylinder device, or a complete heat engine heat pump, that's closed system. If you have a container with fluid coming in and out, that's an open system. A pump alone per se, it's an open system. A turbine does work with fluid in and out, it's an open system. Then you go to the right chapter to analyze the problem, to choose the right equation. I designed 2 problems for this exam. One is, I think, chapter 3, from chapter 3 of chapter 4, involve only first law. I can tell you, chapter 3 or chapter 4, it's a purely first law. Second problem involve, it's a simple problem, but it does involve the use of first law and second law. But for both problems, once you identify the system, determine if it's an open or closed system, go to the right chapter to define the right equations. Let me pull out, I have a summary of you remember I have this handout is still available in the Blackboard. These are the key equations for the first law. You need to dig out the key equation for your analysis. After you dig out the equations, then you can start tackling. You achieve 50% of your goal. This is my grading policy. If you can identify the key equations, start tackling it, eliminate the 0 terms, and then the second half of the analysis usually involves the use of table, property table. How do you estimate the properties? So estimation of the property become important. Okay, this is what I mentioned a few days ago. Identify the system, the state, and identify the right equations. Yeah, there's a linear regression skills you will need. Okay, so this is a procedure, problem-solving skill you will need to have. What else I can tell you? Do I give you enough hint, Mitch? No comment? Are you still there, Mitch? You become quiet. Okay, what else can we do today? I ask you to take the practice exam, mainly to familiarize the procedure today. This is very important. And if you would like me to go through last semester's exam 2, I can go through the exam 2 with you today.
Yes, please.
Okay, let me activate share screen. What else can I share with you? Okay. Now, you already have the problem sheet. Here we have a compressor. Nitrogen is the gas. The inlet stream is fully defined because we know the temperature and the pressure. The exiting stream is fully given. So, and we know how much work is done on the fluid by the compressor. So you already know at this moment the work turn is going to be negative because if we take the compressor as the control volume, there are work done on the compressor. Compressor has to be plugged in to a power source in order to compress the fluid. So we are asked to estimate the heat transfer, specific heat transfer. Okay, so like I said, if we take the compressor as the control volume, we know the gas, then we stipulate the governing equation. This is 100% chapter 3 stuff. Then we eliminate the unnecessary terms in this equation because we can eliminate a lot of terms. We know the problem doesn't mention the velocity of the gas. The problem doesn't mention the elevation change. So these 4 terms associated with kinetic and the potential energies can be eliminated. So the first law reduced to this form. Okay. Okay. Why you may ask why we use this equation involving H, not the equation involving U? Does anyone have an answer? Can you say this is the equation from chapter 3 or chapter 4?
It's for chapter 4. It's an open system for steady state.
Excellent. Did anyone still have doubts? So if you go to the right chapter, I already made a summary sheet here. If you can choose to write first law from this sheet, you get 50 of the points. So this is equation from chapter 4. Because it's an open system. Compressor per se is an open system. It has a fluid coming in and going out. Any discussions? If you don't have question, I can go to the problem number 2. Okay, here we have a P evacuated. Every time I can give you a hint. Every time I see this word P evacuated, I know it's an open system operated under steady state. Okay, if we have a P evacuated, well insulated, rigid container with known volume, is charged with a refrigerant from a continuous flowing system at a given temperature and pressure. So this filling process completes when the pressure of the container reach the same pressure as the delivery line. So we are asked to find the final temperature and the mass of the refrigerant in the container. So we immediately know this is a problem from chapter 4. It's an open system. It's operated in the unsteady state. Filling a tank is an unsteady state problem. And a conceptual question. Do you think the temperature will be lower or higher than the inlet temperature? The answer is it's going to be higher. Before we see the answer, the reason is the fluid in the delivery line has to provide work to push the fluid into the P-evacuated container. If this is the delivery line on the left, this is a P-evacuated container. The fluid outside the container, the fluid flowing, has to provide work to push the fluid into the container. So that's how the fluid going into the container will gain some energy eventually. It's well insulated, so it will gain energy. Energy will eventually become heat. That's temperature. Okay, this is a conceptual issue. So you can make judgment. If your answer turns out to be lower, you know something is wrong. Okay. Then we go to the chapter 4 toward the end. We have a governing equation for unsteady state open system. This is at the time 1, we have this internal energy. Time 2, at the ending state, we have this total internal energy. On the right, we have fluid coming in, carry some enthalpy total energy into the system, plus Q minus W. There's no outgoing stream, so there's no outgoing term like this. complete equation does have outgoing. So this is already simplified. There's no kinetic energy term. There's no potential energy term associated with this. And we also know actually the fluid doesn't do any work, no heat transfer. So this two term can be further eliminated. After you eliminate these two terms, you look at the right-hand side. At the time one, there's nothing in there. So M1 is 0. This term drop out. So we only have this term and this term left. So the resultant equation becomes very simple. U2 equal to H in. And steady state is a very complicated process, but turns out the governing equation can be reduced to a very simple form. Then if you get this equation, you get 50% of the points. This is my grading policy. Then what you need to do is find the property from the property table for the refrigerant. Linear regression will be used. And this is reasonable because this temperature is higher than the fluid in the line, in the delivery line. Then in order to calculate M, we use the definition of specific volume because total volume is given, it's not being used. Divide total volume by the specific volume, we get this. Specific volume can be taken from the property table. Any discussions? So you can treat this, all this problem. You will see this next problem is similar to this in terms of problem solving procedure. There's the same procedure you need to follow. Dig out the right equation. Of course, before that, you have to define what is your system. Then go to the right chapter to dig out the right equations. Okay. Any discussions?
How do you go to table to find the U2 or the H in? Because there is no table entrance for the pressure. You only can find it through temperature, or you can do the linear interpolation to find the H.
Okay. The ending state pressure is given. It's because we know the initial state, the incoming fluid's enthalpy can be found from the table. So U2 is known. U2 for the filled tank is known. So at the ending state, we know two properties too. One is pressure. Pressure is given. U2 is given. So from there, we can find T2.
Now, my question is, we don't have a table for pressure entrance, which means we can't use pressure directly find the U2.
No, from this equation we reduced to this form, right? But H can be found from the table. H is the inlet stream, this fluid in this line. Refrigerant at 90 degrees C3 megapascal. This is from the table.
Okay, I got you.
Yeah, so then we go to the table to find U2 at this value. We found what is the temperature where U2 is at this number and the P is at the 3 megapascal. So that's why you find two temperatures within this range. You can do linear interpolation. Do you have the table with you? Do you want to do this exercise? Can you identify the table?
Table B.5.1.
B.5 is a refrigerant 134. I have a nice addition. So we look at the 3 megapascal. 3 megapascal is 3,000 kilopascal. It's on page 715 in the nice edition. And then we look at the temperature, internal energy. Internal energy is 436. So we know it's between 436 kilojoule per kilogram.
How do you know it's a superheated vapor?
Yes, it's a superheated, yes.
But the question didn't see that.
So we know the temperature is between 100 and 110 degrees Celsius. Do you agree? From
Yes,
table
sir.
B.5.2 on page 715, there's a sub-table for 3 megapascal. So we know the temperature of the ending state has to be between 100 and 110 degrees C. And if you know the theory I discussed, you already know you are on the right track, because this range of temperature, 100 and 110, for make this temperature higher, that makes sense. Any other discussion? Anybody? Okay, if no question, I can go to the third problem. This problem states CO2 in a piston cylinder device. This is the first thing I look at it. What is the system? So if we are talking about gas inside a piston cylinder device, it's a closed system. No mass in, no mass out. It's compressed reversibly. So this would appear, that means second law will be activated. Okay, this is a secret. And also this word isosomally is very important. That means initial temperature equals the ending temperature. So if initial condition is fully given, temperature and pressure is fully given, to saturate the vapor state, is the ending state fully given? I would say yes, because every time you see saturate and the isosomal, so ending state must be at the 20 degrees C also. And the pressure, which is at the saturated vapor state. Okay. Then we are asked to find the work heat transfer associated with this process. So we are asked to answer the two quantity in the first law. But from the word irreversibility, we know second law will have to be activated. And it's a closed system. So we need to look for the governing equation from chapter 3 and chapter 6 for closed systems. The answer I got had some mistakes, so I corrected. Then first law for the closed system, very simple. This is initial state, ending state equal to Q minus W. Second law, we already know for a reversible process, the change in entropy equal to dq over T. Once we realize this, if you can do this, you can do these 3 lines, you get 50% of the point, because the second half rely on couple logistic issues too. How to find the properties from the appendices. Okay, so at the initial state, because states are fully given, I even tell you which page of the textbook you need to look for. From the table, we can find these tabulated numbers. So the property are known. Why do we need to dig out these 2 numbers? Because on the left-hand side of first law and the second law requires this 2. And we have 2 unknowns to be answered. We have 2 equations. Property can be found. And instead, we can also find from the saturated table, because ending state is saturated vapor. So we dig out the numbers from the saturated table. Pretty straightforward. Then Q term can be and so we have 2 equations, 2 unknowns. We solve Q first because it depends on only entropy. Then after Q is found, we use first law to answer the W. Very straightforward to me. If you follow my suggestion of problem solving skill, you should have no problem. Any questions? No questions? So I can stop the sharing. Any suggestion what we should do next? Taylor, you have been very quiet. Are you there?
Yes, sir.
Okay. And do you have questions? Comment? Whatever.
Probably, but I'm still waking up.
What else can we do today? If no, we can adjourn. Can we?
Dr. Chen,
Yes, sir.
for
Ronald.
the homework due today, do we turn that in at the homework submission that was originally due?
Yeah.
was-
Yeah.
Okay.
Yeah.
All right. Thank you.
Sure. Okay, Justin has a message. Go over problem number 4 one more time from the homework. Well, I did not assign homework number 4, did I? Oh, I did. Let me see. Oh, yes, no. Oh, I didn't assign number 4, Justin. I assigned 5, 6, and 8. You raise a second part of the question is good. Justin, did you see number 4 is will be postponed to after the exam? So you worry a little too much. But for those who can do it, it's great. That means you have watched the video already. Justin, are you following? I changed it in the discussion last time. I said to change it to I sent too many announcements. Number 5, number 6, and the number 8. Okay. I think I sent an announcement to everyone. And we discussed some of those questions last time. Do you still want me to discuss those homework? If not, we can discuss when we're going to collect the rest of the homework problems. For chapter 6. We don't have much time left for this semester. How many? Today is 10th. We have 3 more weeks of lecture. My goal is to at least finish chapter 7, which I think is reachable. maybe we can discuss chapter 9 too. We're going to skip chapter 8. So chapter 8 will be a useful chapter for practical engineers. No more theory, just practical applications. Chapter 9 and chapter 11, chapter 9 and chapter 10. Even we're going to discuss a few selected sections. They are practical applications. You email us 347 will be due today. Really? But I remember.
No, sir, you sent email to us, said 3, 4, and 7 will due today.
I made a mistake. I'm sorry if life has been a little chaotic under such circumstances. I learned online delivery. I create the tapes. Very, very crazy period of time.
And on Blackboard assignment, you also announcement. You also said it's problems 3, 4, and 7, not 5, 6, and 8.
Okay. If I did it, I made a mistake. I meant 5, 6, and 8.
But on the help session on Monday, you said it's 3, 4, and 7. So I finished it and submitted.
Same.
In the help session, what did I say? In the Monday, what did
You said change the homework problem to 3, 4, and 7.
Let me write it. In the help session last time, I said number 7 and number 3, 4, and 7.
Yes, sir. First, you want us to finish 1 to 5, and then you change it to 3, 4, and 7.
Yeah, we, just 1 minute. 1 minute. Let me dig out where the confusion comes in. Did I really want to collect number 3, 4, 7 or 5, 6, 8? Okay. I was right. I was wrong today. My goodness. I think this is something you can do. the very first part of the lecture for chapter 6. These 3 problems, 3, 4, 7, can be solved by using the material in the first 1/3 of the material in chapter 6. Chapter 7 may get involved in polytropic process. That may be in the second lecture, part 2 of chapter 6. You agree? Polytropic process. So you're right. You guys are right. I just looked at the email. She's right. She's always right. Uh, 3, 4, 7. That's a deal. 3, 3, 4, and 7. 3, 4, 7. Okay. Justin wanted to look at problem number 4. Number 4, where air is in a piston cylinder device. Initial conditions are given, temperature, pressure, fully given, with a known volume, and we provide electrical power, electrical heat. We know the total amount of energy provided to the gas. The gas remains at the same pressure. Estimate entropy change based on 2 approaches. Averaged specific heat, which is a given, and the tabulated enthalpy data. Okay. For the first part, again, let's use this problem as an exercise. This is do you agree this is a closed system? Justin, you agree? It's a closed system. Justin, do you agree?
I think so, but yeah, we'll have a look at the if work is being added to the system, wouldn't that make it open?
If there is a mass exchange of the system you choose with its environment, then it's an open system.
Okay, then no, I don't think so, because the mass isn't changing from what it looks like.
It's like a pump, pumping a fluid. There's a work done on the pump. So mass there's a fluid coming in and going out of the system you choose. Then it is considered open system. For a gas inside the piston, it's a closed system. So is it the gas inside the container? It doesn't go out, doesn't go in, nothing in, nothing out. So it's a closed system. This is how we define. Can we move to the next step?
Yeah.
Then this problem involves both first law and the second law. If we want to activate the first law, we go to chapter 3. Do you agree? Then what is the key working equation? Can anyone identify the key working equation from chapter 3 for the energy balance portion of the problem?
Is Q equals to delta U plus W and equal to M times H2 minus
Yeah, you see
H1.
insulated, so Q equal to 0. And what does the full equation look like? I can share this. Do you like to share the screen with us? You can write something.
You mean the whole problem? I mean, I can write my procedure down, but I'm not sure I'm right.
So I can share with you. Heat is provided, so the gas expand. But it remains at the same pressure. So this is a question both first law and the second law will be used. Then I can, Krista, did you solve the problem?
Yes, sir.
Do you like to share with us? You can share the screen or write on your whiteboard.
Okay, I can write it down. Okay, share my screen. Can everybody see it? Just wait, let me open my pen. Okay, for this problem, we know we know the volume is 300. And T1 is P1 1 kilopascal, and I think it's Q dot is 200 and watt, and the time and it is ideal gas. And the problem wants us to find the delta S air. What? Sorry. Let me figure out. Okay. You want me to find into massa. Right here. First two method is constant CP and from table. Okay, analyze. Sorry. Analyze. So we first know it's an ideal gas. So we can use the ideal gas law, which is PV equals to mRT. We know P, we know the volume, we know R, we know T. Then we can find the mass, which is PV over RT, is 120 kilopascal times 0.3 meters cubed over. So for R, we go to the table to find this volume. I think it's table 8 point something. I just write it down the number. 287 Pascal kilogram times 29. Okay. Which I got is 0.433 kilogram. And then we know the Q dot, we know the time. We can find Q, which is Q dot times time. And it is, we need to change this union to second. So it's 200 watt times 15 minutes times 16 seconds, 1 minute. What I got is 180 kilojoules. Okay, then we need to use the first law. Delta U plus delta KE plus delta PE equals to Q minus W. Over here, no kinetic energy, no potential energy, they're all zero. Then we can get delta U plus W12 equals to Q12. And then I go to the PowerPoint. I think it's chapter, let me see. I think it's chapter 3 or Anyway, on chapter, I think it's 3 or 2, it had an equation that said H equals to U plus PV.
Right. Excellent. Mhm.
So we plug in here, then we can get, so we use this equation to plug in here, then we can get Q12 equals to M times H2 minus H1.
This is a key step. Yes. Very good.
Yeah, just go to the PowerPoint. I think it's chapter 2 or chapter 3, and you can find this equation and the whole procedure. Then get this equation. You can find it on PowerPoint. And also, it's an ideal gas. It is very important to remember that. So, for an ideal gas, H2 minus H1 is Cp times T2 minus T1. This is also an equation from chapter 3, only for ideal gas.
Mhm.
Y'all can go ahead and look at it. And Cp is a constant which we can find in table 8.5. And I got Cp for air is 1.004. Okay, so all we need to do is plug this number in this equation.
Mhm.
1, 2, Q12 and Cp times T2 minus T1. Okay, so
Very.
we know this, we know this, we know this,
Mhm.
and we know the temperature T1. Then we can get T2. This is for the first method, which is we use the constant Cp.
Mhm. Very good.
And then for calculate delta S, we use the equation from the PowerPoint for chapter 6. Delta S is IM times CPO line T2 minus T1 over T1 minus R line P2 or P1. Then we can get the delta S because we know all the thing, and this term is 0. Because P, I think is because delta P doesn't change. Pressure doesn't change, so this term is 0.
Mhm.
So we end up with CP0 line T2 over T1. Then we can get a final answer.
Excellent. Yeah. Very good. Any discussions?
This is only for the first method. It covered first, it covered ideal gas law, first law,
Mhm.
and closed system for ideal gas.
Yes. Any discussions? Thank you very much, Krista.
No problem. Okay, I stop it.
So, any other discussions? Oh, yeah, homework. The rest of chapter 6, next week we have pretty much occupied by the exam on Monday. Can we collect the next set of homework Friday? We can discuss Thursday. So I will change the recitation to Thursday, maybe. Thursday at 5. Is this a workable plan for everyone? So can we collect the next set? Collect your the rest of chapter 6 next Friday. We can have recitation Thursday at 5 p.m., not a.m. Is this workable? Is this workable to everyone? Okay, then that's a deal. Okay. So please do the practice exam sometime today. Shouldn't take too much of time, just for you to familiarize the procedure, so you don't get the difficulties next Monday. All right. If you don't have any request, we can end our session today at this moment. Is this okay? Okay, there's a comment. Are we turning in the practice test that are we turning in the practice test? Yeah, you can turn in. They are supposed to turn in 2 things. Like I said, in the exam folder, you're supposed to answer short questions. Just sign your name, type your name, that's it. Or you type, I acknowledge the School of Engineering Honors Code. That's what I expect you to do in the real exam. Then get out of the exam folder, but then get into the submission folder. You submit a dummy file to see if it works, how it works. And that procedure is identical to what you did for the homework. I create that folder just like I created for you to submit the homework. So the procedure will be similar. And then nobody else yesterday encountered any difficulty with the submission procedure. But yesterday, there are several students still have problems I have to handle today for the exam. So make sure you take the dummy exam today. Either involve remote monitoring of the exam. That's why some students have problems. And the third folder I created is for in case during the exam, if we have problems, if you want me to clarify some of the problem may be of common interest to everyone, so we can have an open forum. So that's the purpose of the third folder. Okay. So if it's all right, we can end our discussion today now. Can we? You have a good Friday.
You too. Thank
Thank
you for your help.
you. Thank you. Okay. Good luck to your exam Monday.
Thank you, sir. Have a good
Thank
day.
you. Thank you for your help, Krista.
No problem.